So here I'm going to tell you about Michaelis Menten equation. So first of all, before knowing that, the basics of chemical kinetics, a little bit of. So when a substrate is being converted into another product with a rate constant K out here, then I mean, so the rate of the reaction is equal to this and this, because this is getting, this is getting converted to this one, so there's a negative sign. And by the law of mass action, we know that this is directly proportional to A, the rate of the reaction, and that is the substrate or the reactant, and this is the rate constant. So here's enzyme kinetics. So this is the enzyme and substrate combining to form a complex, and then it is getting converted into the product and the enzyme. And so here the rate constant for this one to form this is K1, and for the reversal is K minus 1, and for this one to this one is K2. So as we learned from here that this is directly the conversion of this reaction, from this to this, the rate of the reaction is directly proportional to A, that is the reactant, and here and getting and one multiplying by the rate constant, we get this rate of reaction. So out here, to know the rate of change of this one, we need to first calculate. So its conversion from this one to this one, we need to know that. So for that one, this one, then from this one to this one, that is, it is getting it is getting, what to say, it is reducing. So for that one, negative, this one to this one, and this one to this one is also negative. And then we have now the thing is, ultimately we need to find out this one, because this one actually indirectly tells us about the rate of the whole reaction, because this is a product. So at what rate the product is formed, so that tells us about the rate of the whole reaction. So now out here, the rate of its formation is related to this one, because it is a substrate in this case, it is a reactant in this case, that is forming this. So it is this. And so our target is to find the rate of the reaction, but so this is actually the rate of the reaction, as I already said, of the whole reaction, because this is the product formation, the rate of product formation. But out here, ES is there, but it is not measurable because it is an intermediate in the between. So we need to find the value of ES from this equation, right? Because we have this equation other than this. Other than this, we have this equation. So we need to find out the value of that one from this one. So out here, ES is out here and out here. Okay. But one thing there, it is only one equation, right? And from one equation, if two values are unknown, two variables are unknown, then we cannot find the value of one. But we have out here more than one unknowns. Here E is also unknown, because E is, the active enzyme concentration, that is the enzyme concentration in between the reaction at a particular point, and we cannot know that, right? So that is it. So, but to assume something so that we can find out the value of E or something like that. At least, ultimately we need to find out the value of ES complex. Okay. So first of all, in 1913, Leonor Michaelis and Maud Menten or something like that, what the pronunciation is, they assume that the K1 is much greater than this and they assume that there's an equilibrium at this point. Now they did something I do not know, and their assumption was actually wrong, but that was a pioneering work. So the complex ES, this the enzyme and the substrate together, that complex is known as Michaelis Menten complex. And then in 1925, Briggs and Helden, they assumed that the substrate is much greater than the enzyme. So this one remains constant because, I mean, what to say? Like, when there is excess of substrate, so the maximum number of enzymes are working, but as it only happens, this remains. So the rate of formation of this one is zero. I mean, the rate of this its formation is zero. So this is known as a steady state equilibrium, and until, I mean, at the end or at the beginning for the for the few milliseconds, and at the end when the substrate is about to end, at that time this is getting reduced. I mean, the number of it is decreasing. Now, so here is that equation from that equation number 1. Since this equation is equal to 0, as I said, if I consider steady state equilibrium, so this is it. So there are two unknown variables, so this one and this one. So I somehow need to change this one, right? So we know that the total amount of enzyme we are giving, right? So we can actually, and this one is equal to this plus this, because this is the amount of free enzyme at that time and this is the amount of bound enzyme, so that is equal to the total enzyme I gave. So from that I can get this, and from this I can write this, because this was E, and so this is it. And so out here, and then I'm actually trying to take the constants to one side, and on, since these are all constants, so the ultimately this whole thing is also a constant, right? And they call it Michaelis constant, and so whole this thing is also a constant, and it was named Km, and that's it. Then so this is it. And so we need to find out this one, right, as I already said. So using algebra you can get it out here. And so the rate of the reaction is going to be this, by plain algebra, by calculating from this one, because by putting the value of this one. So now the thing is, when the when the rate of the reaction would be maximum when all the enzymes are working, right, when it is all saturated. So the Vmax, when all the, out here what do we put in case of V? That K and ES, right? That is the complex. So when all the enzymes are being in the complex, at that time it is the maximum speed of working. That's it. So this is equal to this, and on putting the value of this, we get this. That's it. Now that is it. Now the thing is, here Vmax actually does not mean the maximum rate of reaction attended in a particular reaction with time, but here Vmax means the maximum velocity or an enzyme substrate reaction can attain on increasing the substrate concentration. Not only that, it actually also means that of in a particular reaction with time, because the maximum yes, actually means that the maximum, I mean, the max speed of the reaction when all the, I mean, all the enzymes are saturated, the maximum it can go actually. Maybe it is not theoretically actually approachable, but by, I mean, experimentally actually approachable practically, but theoretically it is the maximum, because at that time all of them are saturated. That's it. That's it. Then so with increase in substrate, this the rate increases because at all times some of the enzymes might be, I mean, not working. So on increasing, the working of the enzymes increases on increasing the substrate, and it actually increases in a logarithmic way. That is, the v cannot increase of a certain value as the rate of the reaction of the rate of increase of v decreases, as double differentiation of v actually is negative. Wait a second, negative, or yes, it is negative. That is, this part actually decreases and this whole thing is becomes negative actually. Whole thing becomes with increasing concentration of substrate. But here V can be considered to be a rate of reaction which is variable with time for a particular ongoing reaction, as it is dependent on the active mass of the substrate, that is this S, and the active mass varies with time as the reaction progresses. I hope you are understanding. I mean, that's it. So it is better to calculate it with respect to the substrate, as much substrate would be added or removed in between the reactions. And that's it then. And why this one is not equal to this when this is equal to this? Then how this? I mean, I actually asked the question that, I mean, when this one is equal to this, I thought that this one is would be equal to this, and then why not this one equal to the max speed? But out here, actually the thing is, when it is equal to this one, it is not equal to this because of equilibrium attained before, because this one tends to this when the substrate is infinite, but since the relation is logarithmic, so it tends to be close to this one, or this one close to this one, but never that this particular absolute value. So this is it, because it is actually asymptomatically process this. And so the significance of Michaelis Menten constant, when this one is equal to this, from that equation, this equation, and putting the value of km out here and here, then we get this part, we get 1 by 2. So at that time the rate of the equation, this becomes this, and this is substrate concentration when the velocity is half of the maximum. Okay, and then the low value of Km actually means maximum catalytic efficiency of low substrate concentration, because okay, let me show you the graph actually. So here is the graph. Now the thing is, if this came, if the, so out here in the y-axis we have the velocity or the rate of the reaction, and out here we have the concentration of the substrate. So the thing is, if I mean, if the km is low, so at lower concentration of substrate, so the value of this one is low. So at lower concentration of substrate, we can attain the same velocity, right? So for that reason, if the value of km is low, so then the maximum catalytic efficiency at low substrate concentration can be attended. So that is the graph. And this km is actually unique for a substrate enzyme pair. That is, for a particular enzyme, even if the substrate varies, then this km varies, and even for a particular substrate, if the enzyme varies, even then the km varies. And the km is also dependent on pH and temperature. And so as we last saw that, wait a second, so we saw that we took this to be the km, right? So from this we get this. So and what is this? If we look into the reaction again, so this is it. Right. So this is actually the dissociation constant. This is the backward reaction, this is the forward. So this is the dissociation constant. Sorry, yeah, the dissociation constant. Yeah, this is the dissociation constant, because see, this is the side, from this side to this side is dissociation. So up is this k minus 1. So this is the dissociation constant. So we can write this from the dissociation constant of the Michaelis constant complex, sorry. And so if km is low, that indicates this. Ks is low, that indicates that the affinity for the enzyme for substrate is high, because this is a dissociation constant, right? Dissociation means constant of opening. So if this one is low, that means the affinity for a substrate is more. And this happens when this part is low. At that time it is much more relation. The relation is more comparable, because yeah. And so this is the thing, when this one is much less than this one. And this also means, since it in its denominator has this one, and it too has, so it means that when this is lower than this, much lower than this, that is what it's written out here. So what is this k2? Let's see it again. When this one is much lesser than this one, okay, so that is it. That is, the formation of this one is lower than this one. At that time we can consider it. That is, this, we can consider this to be in relation to this, to be predicted, to predict the enzyme affinity for substrates. And see out here, we can draw a straight line. What can we do out of this? When we're getting a sort of this sort of curve, so we need a straight line to calculate things, right? And previously what we did, that we kept the substrate in the x-axis and the rate of the reaction in the y-axis. So I'm just trying to get the substrate out. So on doing algebraic, on using algebra, we can get this. Algebraic operations, we get this. And to get this part up, I just inverted this, then put it in the x-axis. Thought of putting it actually, and thought of putting this v in the y-axis. So to get this, we just, since we're putting it in the x-axis, so to get this form, this one in this. So from here we can get that this one is the, if this is the x-axis, this is the y-axis, then this is the inverted, this is the reciprocal of the slope. So the slope is this, and the k, and this is the y-intercept by m okay, by the slope. So the y-intercept is 1 by vmax. So here we get this. So since the y-intercept is this 1 by vmax, then the slope is this, and this is the x-intercept. How did you know that? Because out in this case, this is out here, or if we put 0 in case of y, then we get that x equal to this minus this. So this is it. And what some more is there? I forgot. And so to put it in this format, just to show you, I mean, in this format we can write it in this way by algebraic operations. And when these are plotted, it is known as linear Weber-Borg plot, double reciprocal plot. So this is a method to determine the Vmax and Km. So see, from the y-intercept we can get the Vmax, and from the slope we can, since we know this already, we can calculate this. I mean, calculate the value of Km. So that is it. I'm feeling very hungry. It is 19 in the morning. Okay, so the best, I mean, to get the best estimates is the substrate must be calculated from this to this, 0.5 km to 5 km, this range we call it. And then the disadvantage of this plot, most experimental, the substrate gets crowded on the left side of the graph. I do not know why. Well, that is it. And for small errors of ES, I mean, a small error in, for small values of S, a small error in V lead to a large error in this one, and hence a large error in this too. Now, why small error in S? Now, to understand that, see out here, for a small value of the active mass of substrate, here the slope is high, I mean, that is the rate of change of this is more. So for a small change in this one gets, for a small value, for small values of this one, if this one is taken wrong, then it gives a very wrong value of this one and this whole thing, because out here the rate of change of velocity of the reaction is very high. For not the rate of change of reaction, sorry, here the rate, the value, I mean, here the, I mean, this, here the change, yeah, the change in the velocity is very high, or the rate of the reaction is very high in the, for the lower values of substrate. That's it.